All right, so 3.4, the last section before we test on chapter 3 so far. This is called concavity. Concavity, that's what the kids in Mexico City say after Halloween when they go to the doctor. And the second derivative test. The second derivative test. What are you doing? Get away from me. It's sticky. That's gross. All right, concavity and the second derivative test. So pretty much everything we did in 3.3 with the first derivative, we're going to do the exact same thing in this section, but with the second derivative. So it should go pretty easy. All right. If we know on some interval from the previous section that the derivative is positive on some interval, monotonic positive, what does that say about the function on that interval? That the function is increasing. Yeah, and because the derivative is defined, it's increasing how? Smoothly, right. Because it's differentiable, it's increasing smoothly. So what we're going to learn in this section is to figure out how is it smoothly increasing. So here's three different options. If you know that a function's derivative is positive on an interval, then that function could be either increasing like this, or it could be increasing like this, or it could be increasing like this, right? In all three of those scenarios, the first derivative is positive, yes? But they're very, very different. In this case, this one is increasing at a constant rate, and this one is increasing at an increasing rate, and this one is increasing at a decreasing rate. So if we are going to then be determining how something is increasing or decreasing, the rate of change of increase, decrease, we're going to be looking at how the derivatives are changing, right? How the slopes are changing. And that's going to require not the first derivative of f, but the second derivative. The second derivative of f tells you how the slopes are changing. Okay, so in this case, the slopes aren't changing. The slopes are constant all the way through. In this case, the slopes are whatting? The slopes are increasing, right? You have like a positive slope there, a positive slope there, a positive slope there, but as you go from left to right, they're getting bigger and bigger. So if the slopes are increasing, the graph is going to be increasing at an increasing rate. In this case, the slopes are decreasing. Yeah, so we have a positive slope, but they're getting smaller. So it turns out that when you analyze how the slopes are changing, that is, when you analyze the second derivative of a function, you are analyzing how the graph is curving, okay? And if the second derivative is 0, slopes are constant. If the second derivative is 0, the graph has no curvature. In this case, the graph does have curvature. The second derivative is going to be positive. Okay, f double prime is going to be positive because if the slopes are increasing, f prime is increasing, which means f double prime is positive. And if the slopes are decreasing, then f prime is decreasing, which means f prime is less than 0. And I guess I should come over here and say f double prime equals 0. So the second derivative gives you the curvature of the graph. In this class, we can refer to it as curvature, but the term that is most often used is concavity. So the concavity of a graph and the curvature of the graph are referencing the same thing. Curvature is concavity, concavity is curvature, right? Got it? And if you have a second derivative value that is non-zero, you will have a curve in the graph. All right, so here's the important idea. If f prime tells us how the y values of a graph are changing, then the derivative, bless you, of f prime tells us how the slopes are changing, and that's f double prime. So here's the relationship between f double prime and the concavity on an interval. If the second derivative is greater than 0, that would be like this case right here, we say the graph is concave up. And you can kind of have a little mnemonic here, like a cup. See that cup and up, they rhyme. Up like a cup, right? Up like a cup. And that means the slopes are increasing. If the second derivative is less than 0, that would be like this one here. Then we say the graph is concave down, not like a downward opening cup, but like a frown. Concave down like a frown and concave up like a cup. That means the slopes are decreasing. And if the second derivative is equal to 0, then F has no curvature or no concavity, then the slopes of F are constant. It's a straight line. All right, so here's an easy way to remember it. These are some memes, right? Concave up like a cup. So if you take the old smiley face and you give them plus signs for eyes, the plus signs represent positive concavity. It's going to be up like a cup. So he's smiling. It holds water. See, there's the water that it's holding, purple water. Looks like a weird mustache. Now, you can actually have the graph being decreasing concave up. Oh, that didn't work. Held it too long. Decreasing concave up or increasing concave up. So any part of a smile is concave up, right? Any part of a smile is concave up. Similarly, concave down like a frown. Y'all know Walter, right? Yeah. His eyes are beady eyes. They're almost like negatives, okay? And so like Walter, you get concave down like a frown. So anytime the second derivative is negative on an interval, the graph is going to be concave down. Now, it could be increasing concave down or decreasing concave down, either one of them. And then if you have 0 for your second derivative, then maybe you're filled with angst and you have a hockey puck smile. You have curved depravity, right? It's straight. Okay. Some memes are better than others. Very good. Yeah? Walter there will be performing at the San Antonio Talk Show. Oh, nice. Nice. Yeah. Maybe you go watch him and you heckle him with calculus and see if he can tolerate it. All right. So because we can have concave up with decreasing or increasing, and we can have concave down with increasing and decreasing, now if we can decide on any given interval what the sign of both F double prime and F prime is, we'll know what the graph looks like. Okay? Combine that with the F values, the Y values, and now you can put the graph in the right location, and you can have it doing the right thing. So if you take a circle then, and you partition it into 4 different pieces, on any given interval where the graph has curvature, it's going to be doing one of these 4 things. Okay? One of these 4 things. If it's looking like that, this would be increasing concave what? Yeah, concave down. I'm going to abbreviate concave as CC. You can abbreviate all year long until May 15th, in which time you write out concave. So this would be increasing concave down. So if it's increasing concave down, what's the sign of the first and second derivative? Positive and negative, respectively. Yeah. Okay? If you slide over to the right, this little piece of the graph is now decreasing concave what? Concave down. It's part of the frown again. So what are the signs of the first and second derivative, respectively? Negative, negative. Yeah, if both the first and second derivative are negative on an interval, you know it's decreasing concave down. And you would draw it like that. All right, on this little interval, bottom left, now you have the function decreasing, and it's concave up like a cup. First and second derivative then are going to be negative, positive. Yeah, good. And this last piece here, this one is increasing concave up. So the first and second derivative now are both positive. Cool. Positive. All right, so we need a new definition now. We need a different type of x value. An x value where the derivative is 0 or undefined in the domain of the function is a critical value, right? Critical values then become the places where a graph can change its increasing, decreasing behavior. We need to come up with a name then for a value where the graph can change its concavity behavior, concave up or concave down. So let's jump to that. Definition. An x value, call it x equals p, in the domain of the function is said to be an inflection value of f of x if the graph changes from either concave up to concave down at that x value or concave down to concave up. Okay? So an inflection value is analogous. An inflection value is analogous to a local max or a local min location. Okay? Local max and mins only occurred at critical values, but not every critical value was a local max or min. Same thing here. If the graph changes concave up to concave down or vice versa, it's going to be an inflection value. But the places where that can happen might not always be an inflection value, just like not every critical value is a local max or min. what we're going to do to justify is like we did with the first derivative test. We're going to talk about a sign change in the second derivative. If f double prime changes from positive to negative, then the graph goes from concave up to concave down. And if f double prime changes from negative to positive, the graph goes from concave down to concave up. Okay? So here are some examples. Here's a continuous function. We have the graph being concave down to the left, concave up to the right. And so right there we have an inflection value, or an inflection point if you consider the y value. It changes its curvature there. Over here, we have a graph that is concave up to the left and concave down to the right. So since the curvature changed there, we call that point an inflection value. Now notice it's also a local min. Over here it wasn't a local min. So local extrema can also be inflection points, right? There's an example of one that's both. Here is one where it's concave up on one side and concave down on the other. Is that going to be an inflection value? No, this one is not an inflection value. I'm going to call that an IV, okay, for short, like a CV, okay? But it potentially could have been, right? It potentially could have been, because that could have easily been concave up on one side and concave down on the other. It looked like a shark fin, but it wasn't, okay? So let's look at this last example here. This is concave down to the left and concave up to the right. Is that going to be an inflection value? No, also not an inflection value. Why not this time? Yeah, because that point is not in the domain of the function. So just like critical values are possible places where local extrema can occur, we're going to come up with a name for something that could be an inflection value. Okay? And also similarly, just like a function can change from increasing to decreasing at a discontinuity that's not in the domain of a function, same thing here. A graph can change its curvature at a place that's not in the domain, like a discontinuity. All right, so here's the next definition. And this is my definition. This is not really like in any textbook, but you got to give a name to it. I call it a possible inflection value. That's a pretty good name, okay, which is a PIV for short, possible inflection value. Now, if you don't like possible, you could say prospective, potential, something like that with a P. It's a possible inflection value. It's going to be a value in the domain of the function f of x where either the second derivative is equal to 0 or the second derivative is undefined. In this case, a PIV is analogous to what? A CV. Good. Analogous to a CV. A CV is a possible local max or min. A PIV is a possible inflection value. And just like with the first derivative, we want to know where the second derivative is 0 or undefined. Now, why does that work? Let's look at this right here. If this graph goes from concave down to the left to concave up on the right, then that means the second derivative is negative on one side and positive on the other. Through a continuum, guess what value the f double prime has to pass through when it goes from negative to positive? It has to pass through 0. So right there, the value of the second derivative is equal to 0. Okay? That's where the second derivative would equal 0. Right here, what would the value of the second derivative there be? It's undefined, right? Why is it undefined? Well, is the first derivative defined there? No. If the first derivative is not defined there, there's no way the second derivative is going to be defined there. Okay? Because you can't take the derivative of something that doesn't exist. And that ended up being an inflection value, right? The curvature changed there. Here's another place where it was a possible inflection value, but it didn't turn out to be an inflection value. And of course, anytime you have a discontinuity, you're going to want to test on either side of that as well, because the curvature can obviously change there. Okay? So it's really, again, analogous to what we did last time. Let's go ahead and write this. And I'll use the old analogy syntax. A possible, well, let's back it up this way. Let's do a CV is to a PIV. No, we'll do it this way. I'm sorry. A CV is to a local extrema. This will work. As a PIV is to an inflection value. Now, y'all probably haven't seen this notation. Do they still use this in an English course? Yeah. Okay. This used to be on the SAT, and they got rid of it. Butter? What does butter mean? Local extrexa. Oh, local extrexa. What is that, extrexa? That sounds like a new pharmaceutical that has like 100 side effects that you're trying to ask your doctor about to take care of your blood pressure or something. New extrexa by Bristol Myers Squibb. Thank you. I meant to say what? Extrema. There you go. A CV is to a local extrema as a PIV is to an IV. Yeah. So kind of a lame little thing there on the end. PIV is to an IV. But there it is. It's pretty much the exact same thing. And discontinuities always have their place in any kind of number line chart. So here's the theorem. The graph of a function can change its concavity at only one of two places. Where can a graph change its curvature? At either a PIV or discontinuity. Very good. Either at at a possible inflection value or discontinuity. And an inflection value can only occur at a PIV, just like an extrema can only occur at a critical value. But not every PIV is going to be an inflection value, right? That's why we have it a P in front. Possible, prospective, potential. Okay? We saw that example right there. That was a possible inflection value, but the curvature didn't change. So what we're going to do is now test for the intervals of concavity like we did originally with testing for intervals of increasing, decreasing. It's the same idea. We're going to find any discontinuities in the function. They have their place in the chart. We're going to identify any of the PIVs that, of course, are in the domain of f of x, the values that make the second derivative 0 or undefined. Then we're going to make a number line chart, and we're going to test the intervals between the PIVs and the discontinuities, if there are any. And we're going to test the sign of f double prime, the sign only. If the second derivative is greater than 0 on the interval, the function's concave up. And if the second derivative is less than 0, the function's concave down like a frown. All right, so we always start with a nice, easy little graph here. The graph of the function is defined everywhere on the interval from a to k, closed interval. List the possible inflection values. All right, is a possible inflection value? Well, let's see. Is it in the domain of the function, a? Yes. What's the value of the first derivative there? Doesn't exist. So what would be the value of the second derivative? It would also not exist. So technically it is a PIV, just like it's technically a critical value, but it's not going to be a local extrema, and it's not going to be a change in curvature because you don't know what it was to the left of that. Okay, but it is a PIV. So we have PIVs of x equals a. Is b a PIV? This one's kind of hard because you don't have the equation, so all you have to do is look to see if it's an inflection value, then of course it's going to be a possible inflection value. It's concave down to the left and concave up to the right, so it must pass through 0. So B is, of course, a PIV. What about C? It looks like it's concave up to the left and concave down to the right. So, of course, if it's an IV, a full-fledged inflection value, it's going to be a possible inflection value. What about at D? Concave down to concave up? Yeah, that's going to be a possible inflection value. What about at E? Is it a possible inflection value? Yes. It is, because the first derivative is undefined, so is the second derivative. It's in the domain, so it's a possible inflection value. What about H? Yeah, it's in the domain, right? That's good. Because the first derivative is undefined there, so is the second derivative. So that's another PIV. And what about K? Yeah, technically the endpoints work as well. Now it says that each of those determine if F has an inflection value and justify. I'm not going to write out the justification, but we'll talk about it. All right, so now we have actual IVs at x equals. Is A an IV? No, because there's no way to determine if there's a curvature change, because we don't know what the curve looked like before A. What about B? Yes. Now here's what you'd say. F has an inflection value at B since F double prime changes from what? Negative to positive at x equals B. So it's pretty much the same recipe for local extrema justification. You don't say since F changes from concave down to concave up any more than you'd say F goes from increasing to decreasing. You talk about a sign change. F has a inflection value at x equals B since F double prime changes from negative to positive at x equals B. Good. What about C? Inflection value, yes or no? Yes. since f double prime changes from positive to negative at x equals c. This is after you've declared them to be possible inflection values. What about at d? Yes, since f double prime changes from negative to positive at x equals d. What about at e? No. And again, you would say since f double prime is positive on either side of e. There was no sign change in the second derivative. What about at h? Yes, h is an inflection value. It's also a local max, right? But it's an inflection value because, again, f double prime changes from positive to negative at x equals h. And what about k? No, it's an endpoint. Don't know what's happening to the right. Okay, so that's one way to use the graph. The other thing, list the open intervals where the graph is concave up, concave down, or constant. All right, so f is ... cc up and cc down. cc up on, well, we've got it. What's the first open interval? It's that open interval for cc up. B to C, union, D to E, right? Union. Could we go D to H? That's a very good question. I was just going to ask that. What is the concavity value at E? Unfortunately, it doesn't exist, right? So you would have to step over it because technically there is no curvature at that single point. Yeah, good question. And I think that's it for the up, right? Concave down, that would be on the interval from A to B, union C to D, union H to K, right? So not very difficult. If you have the graph and you have those marks conveniently labeled for you, it's pretty easy. What we're going to do, though, is we're going to find it analytically with an equation. All right, so important idea is to reiterate, which means to iterate again. What does iterate mean? To repeat, right? So when you reiterate, you're re-repeating. Not every PIV is an inflection value, just like not every CV is a local, what did I say? What drug was that? Extrema. No, not it. Extrexa, yeah. Concavity can change at either a discontinuity, such as a VA, but it won't be an inflection point if it's not in the domain. To find possible inflection values, right? We're going to look for all the values in the domain of the function where the second derivative is 0 or undefined. And then the number line chart can help you effectively or efficiently and effectively determine the sign of f double prime between any PIVs and any discons. Here we go, example 4. For each of the following, find the PIVs, the inflection values with justification, and the intervals of concavity. All right, here we go. What's the domain of this function? All real numbers. That's good, because now any value that happens to make the second derivative 0 or undefined will be a PIV. We need the second derivative. We got to go through the first. So y prime is cosine of x. Y double prime is negative sine of x. And just like we would for then critical values, you want to consider first, where is the second derivative undefined? Where is negative sine undefined? Never, right? So you're not going to get any solutions there. Where is the second derivative equal to 0? Well, that's when sine is equal to 0. Sine is equal to 0 from 0 to 2 pi when x is 0, 2 pi, and pi, also pi. And we're including 0 and 2 pi because it's a closed interval. So we have 3 PIVs. Now we set up our little number line chart. So here we go. We got x and now y double prime. Any discons to put in the number line chart? Nope, none. So we just put these in order. Well, 0 is right here. 2 pi is right here. Remember, since the interval is specified 0 and 2 pi, we don't want to choose anything to the left of 0 or to the right of 2 pi. So they're endpoints, but we're not going to really be affected by them. As long as we choose something to the left of pi that's not to the left of 0, and something to the right of pi that's not to the right of 2 pi. We are going to be plugging it back into the full-fledged factored version of the second derivative now, the full-fledged factored version of the second derivative. All right, so what's a nice, we're going to take the sign values, keep that in mind. What's a nice value to the left of pi? Pi fourths will work, pi sixths will work. I'm going to choose pi halves. A little bit easier, I think, but feel free to choose whatever you want. And between pi and 2 pi? 3 pi halves. Just because I know I'm taking the sign, and I know that at the odd pi halves, sign has pretty values. All right, so now it's negative sine of pi. So here's where you want to be careful. If you took the original second derivative, thank you, negative sine of x, and you set it equal to 0, in the process of solving for x, you might multiply both sides by -1, like we did. You can't plug it back into this version, right? So be careful. You got to plug it back into the fully intact version, which is negative sine. So what is negative sine of pi halves? Positive or negative? It's negative. Good. And then negative sine of 3 pi halves is positive. So just like the first derivative number line chart gave us 2 pieces of information, intervals of increasing, decreasing, and or local extreme of info, this graph or this number line chart gives us concavity intervals as well as what we need to justify inflection points. So here we go. F, or is it Y? It's just Y. Y has an inflection value or an inflection point at x equals pi, since what? Y double prime changes, good, from negative to positive. Not in France, but at x equals pi. Now, real quickly, did it ask you for the PIV? So it didn't ask for the inflection points. If it asks for the inflection points, you need the Y value as well, which you can get by plugging back into the original. All right, so that takes care of that question. And now intervals of increasing, decreasing, that pretty much comes for free as well, right? So here we go. Make some more room. Y is CC down on the open interval from where to where? 0 to pi. And that's where you have to be careful. You can't just say for x less than pi, right? If you're ever given a closed interval, you have to keep that in mind. And Y is CC down, or CC up, sorry, we already did down, on the interval from pi to 2 pi. Yep. And of course, you could easily sketch the graph of 3 sine of x and verify that that's true. In fact, 3 sine of x looks like this. Here's 3. It goes all the way up to 4 and all the way down to 2, and it's the hala. It looks like that. Here's 2 pi. And there is pi. Yeah, so you can almost answer that question just using pre-calc knowledge instead of calculus. But it's nice to know the calculus method gives us the same information. All right, so it kind of has a deja vu feel to it if you've done your 3.3 work. All right, this one here, same thing. Got to figure out what the domain is first. What's the domain of this function? Yeah, all real numbers, good. That's the same as 6 over x squared plus 3. So even though it looks like we might be at risk for dividing by 0, it's not going to happen because x squared plus 3 is 3 or bigger. It's never 0. So we're good. Now let's go ahead and find the second derivative by going through the first. I'm going to go back to the original version, right? Rather than the Hody-High rule. The chain rule is a little bit faster. So f prime, -6 blob to the -2nd times the chain rule, 2x. So if you clean that up, then you get a -12x times x squared plus 3 to the -2nd. From there, you can either use the chain rule and product rule, or you can use the Hody-High rule. What do y'all want to do? Chain rule? Okay. So f double prime starts with the product rule, right? So we got -12x. So the derivative of that is -12 times the second one goes along for the ride, plus -12x or -12x times the chain rule again, which is now going to be -2 times x squared plus 3 to the -3rd power times another chain rule of 2x. So just like with the first derivative, our goal is to put it into a single fraction factored version, a single factored fraction version. So what we're going to do now is factor out least powers and possibly a number, okay? And maybe we'll factor out the negative. That looks good. So I'm going to factor out a -12. And then an x squared plus 3 to the what power? Negative third. Good. And this is an occasion for the beefy brown bracket. There we go. So in the first term, we are left with no numbers. The negative 12 came out. And remember, when you subtract exponents, negative 2 minus negative 3 is really negative 2 plus 3 or 1. So you're just left with x squared plus 3. You don't even need to put parentheses around it. In the second term, we're left with the negative, or we're left with, okay, that negative 12 is gone, and all of that's gone. So we're just left with the stuff that's not highlighted. So it's a 2x times a negative 2x, which is a negative 4x squared. Yeah, this x. Yeah, that one's still there. So that x times that x is x squared. And then 2 times negative 2 is negative 4. Yeah. Yeah, it's very carefully taking inventory. But if you can handle that step, it again is the fastest, cleanest, most efficient way to put it back into the final form that we're looking for. So you'll end up with a negative 12 on the top. And now if you combine everything in the beefy brown brackets, you're going to get a negative 3x squared plus 3. And at the bottom, you're left with just an x squared plus 3 cubed. And I'll simplify one more time here. F double prime of x. What else can I factor out now up here? A 3 or maybe even a negative 3. So when I factor the negative 3 out times the negative 12, that makes it a positive 36. And then I'm left with an x squared minus 1. And so this is going to require a little bit of work. The first derivative required work. The second derivative, of course, as you can imagine, is going to require even more work. But getting it down to this point is going to be well worth it, because now everything should go a lot more smoothly from here. We can identify the PIVs, and then we can use this to determine what the sign is going to be. Now, x squared minus 1, if you want to factor it as the difference of squares, that's not a bad thing to do. All right, I'm going to borrow the space down here. Sorry, e to the negative x squared. PIV. So first, f double prime is equal to dne. Ever? Well, yeah, when the denominator, x squared plus 3 cubed, is equal to 0. But is that ever going to happen? No. So there's no solutions to that one, or no PIVs. F double prime is going to equal 0 when the numerator is equal to 0. When 36 times x squared minus 1 equals 0, which once you write down the numerator equal to 0, then you can just rattle off the two solutions. What are they? Plus or minus 1. So those are your PIVs, possible inflection values. All right, so now we're ready for the number line chart. Do we have any discontinuities? No. And only 2 PIVs, so that's going to give us 3 intervals to test. We got a negative 1 and a positive 1. Let's see, some values, negative 2, 0, and 2. I like those. And we're plugging them back into that version of f double prime. What do you know about the denominator? It's always positive. Yeah, so you don't even need to bother plugging in there. 36 is always positive in the top. So really the sign of the second derivative is determined exclusively by x squared minus 1. But when in doubt, go ahead and just plug it into everything. But sometimes it's faster if you can make those associations. So when you plug in a negative 2 for x, you're going to get a positive number. When you plug in a 0, you get a negative. When you plug in a 2, you get a positive. So now it's just a matter of stating our results. I'll just say it. I don't think I'll write it. F has an inflection value at x equals negative 1, since f double prime changes from positive to negative at x equals negative 1, and at x equals positive 1, since f double prime changes from negative to positive at x equals 1. So they're both inflection values, right? But if you're asked to justify, since they both change signs in a different fashion, you have to separate the justification, okay? Because you always have to say how the sign changes. And then if we wanted intervals of increasing, decreasing, we said the domain was all real numbers. There's no interval given, so you can actually say that f is concave up everywhere to the left of negative 1, right? Everywhere. So like for all x, or negative infinity to negative 1, union 1 to infinity, and f is concave down on the interval from negative 1 to 1, okay? So I'm not going to write all that out, but that's what it would be. Okay, we're just practicing second derivative information right now, but if we wanted to, we could then come back up here to f prime land and do all the work we did in the previous section, and then combine the results. And once you have the local extrema values and the inflection values, you could plug them back into the original function to get the y values, and now you have a specific location to plot all that stuff, and then all you'd have to do is come back and connect those dots with one of these 4 types of lines, right, or curves, and you'll have the graph. That's where we're heading. That's where we're heading. That's the next section, 3.5, where we put it all together. Right now we're practicing in isolation. All right. Not sure if we have to do every single one of these, but let's do C, because it comes next. If you get in the habit of analyzing the domain first, you're more likely to have success throughout the problem. What's the domain of this one? All real numbers? No. It'll be the set of all x such that x ain't what? Plus or minus 2, yeah. Just for the record, are they VAs or wholes? They should be vertical asymptotes, right? Because when you plug your plus or minus 2 in the top, you get 5. And non-zero over 0 is vertical asymptotes. So even if they were wholes, it doesn't matter. They would still get their place in the number line chart. So we already got 2 values in our number line chart, namely 2 and negative 2. And I'm going to draw them as dotted lines eventually, but we're not there yet. Now we need to find the PIVs. That's when the second derivative is undefined or 0. I wish there were a way to go straight to the second derivative, don't you? No, there's not. Good thing, though, because you wouldn't want that anyway, because you'd have about half the fun. Half the fun is going through the first derivative. Okay, it's courteous to say hi on your way by. G prime of x, ho-de hi, ho-de hi. Ho, d hi, minus hi, d ho, all over ho ho. Now, would you want to jump right into the second derivative based upon that version of it, or you want to simplify before we? Yeah, me too. So remember that when you do the quotient rule, it essentially is partially factored, or you look to see if you could pull out common factors first. Because just expanding it all out with the attempt of trying to refactor it might be counterproductive if it's already partially factored. We have a factor of 2x already that's common in both those terms. So let's factor out the 2x, and we're left with an x squared minus 4, and then a minus quantity x squared minus 1, which is going to be minus x squared minus 1, all over x squared minus 4. Now we'll clean that one up again, and it looks like your x squareds cancel. Oh, that's sweet. And you're left with negative 5 times 2, that's negative 10x, all over x squared minus 4 squared. So that's a pretty handsome version of G prime. It's ready to go to find your PIVs. It's ready to go to test for number lines for local extrema and intervals of increasing and decreasing. But we're not focusing on that right now. So now we're ready for G double prime. And we can either use the ho-de hi rule, which always gives us a single fraction, or bring it to the top and use product chain. I like ho-de hi here. So here we go. G double prime. In this case, it's probably just easier to let the negative be associated with the 10x in the top. So ho, d hi is negative 10. Minus hi, minus negative 10x. D ho. D ho is going to require the chain rule. I need a little more room. So remodel. There we go. You get 2 x squared minus 4 to the first times 2x. All over ho, ho, which is now ho to the fourth. Okay, so the good news is it's already a single term, right? One big fraction, bless you. But it's not in the cleaned up factored version that we're desiring here. So a little bit of housekeeping in the top. Now I have 2 terms, and I have an x squared minus 4 that's common in both. And I also have a negative 10 that's common in both. See that? So I'm going to factor out an x squared, or actually let me put the negative 10 first. I'll factor out a negative 10, x squared minus 4 to the first, and then the beefy brown brackets, respect. In the first term, this one right here, we're just left with x squared minus 4. Yeah. And in the back, we're left with everything that's not highlighted, which is going to be a 2x times 2, which is 4, and a 4 times a negative x is a negative 4x squared. Negative 4x squared. That's you got to be careful with that. Negative 2 times 2x is negative 4x squared, yeah. All over x squared minus 4 to the fourth. Now you have an option here. You notice there's a common factor of x squared minus 4. If you want to divide it out, that's fine. But now your denominator is going to be cubed, which means it could be positive or negative. If you leave it in there, the bottom's always positive, so you don't have to worry about it. If you were to look at getting roots from this, making g double prime 0, they're already off limits because that gives us the two vertical asymptotes. So I would probably divide it out. That's what I would do. So with one of those dividing out, leaving that a cubed, you're now left with negative 10 times, and then in the beefy brackets, you're left with negative 5x squared minus 4. All over x squared minus 4 cubed. There's going to be quite a bit of housekeeping or algebra in getting these things into that pretty format. Sorry, x to the fourth, I'm going to borrow the space. I'm going to do one more thing, because you got negatives all over the place up at the top. If you factor just the negative out, it would be positive 10 times 5x squared plus 4 all over x squared minus 3 cubed. And that is what we coveted, right? Not our neighbor's possessions, but our own second derivative. Why did it turn to 3? I don't know. That was there we go. Thank you. Is the top supposed to be? Yeah. Because I crossed it out and made a 3 there, and then I put a 3 inside instead of just out on the outside. Okay, so that's good. Now let's go ahead and find the PIVs. G double prime is equal to DNE. Is it still messed up? Is it still messed up? It's supposed to be a 3. Negative 3x squared. And I put negative 5. Negative, that's hasty making wasty. And so that should be a 3 right there. Okay, sweet. How's that look, guys? I'm trying to come on before we take a stand. I'm kind of nervous. I don't want to mess up the recording. Get the random weather report. Okay, don't rush. Okay, take a deep breath. Haste makes waste. Don't make waste. Don't make haste. G prime equals DNE only when x is equal to plus or minus 2. Well, that's when the denominator is 0. Are those going to be PIVs? Nope, because we already identified them in the beginning as vertical asymptotes. They have their place in the chart, but they're not going to be possible inflection values. G double prime is going to equal 0 when the numerator is equal to 0. When is the numerator equal to 0? Never. All right, it's 40 at the very least. That's pretty safely away from 0. So all that freaking work for nothing? No, for something. To conclusively state that there are no PIVs. Right? We could say it conclusively, there are no PIVs. All right. Does that mean that the graph has to be concave up or concave down over its entire domain? No, because where else could it change? At the asymptote. So if there's no PIVs, there's no IVs as well, right? No inflection values. Can't be. But we still have an interval to test. We've got x and f double prime at the vertical asymptotes. Negative 2, 2. Dotted or dashed lines, or a combination of, because they're discontinuities, right? Dashed. All right, so we're plugging it back into the top up there. So we're picking our test values of negative 3, 0, and 3. And we plug them back in up here. And I called it F instead of G. It gets better and better. There we go. Now, when I plug these test values in, I don't need to plug it into the top, because it's always positive. And I don't need to bother cubing the denominator either, because when you cube something, you preserve its sign, right? Okay, good. So it just comes down to x squared minus 4, which if you know what the graph looks like, you probably have the answer. But let's just plug it in. The sign of the second derivative is determined uniquely by the x squared minus 4. So you're going to get a positive and a negative and a positive. Okay, there you go. So now, without writing it, we could say it. G is concave up from negative infinity to negative 2, union 2 to infinity, and G is concave down between negative 2 and 2. Do we have any inflection values? No, they're vertical asymptotes. Okay, so discontinuities are pretty important. Now look at all that wonderful algebra right there. That is good stuff. If you could track through that and follow all that, that's good. Especially to catch a subtle mistake like that. That's pretty good. That looks like something you might see like under a bridge, right, somewhere with like spray canned on, just like cool math graffiti. But unlike like in Hollywood, when you see math graffiti, it doesn't mean anything. It's just like gratuitous symbols all over the place. This means something, right? You'd be walking under the bridge, you know, trying to sneak in somewhere, and you're like, oh man, yeah, that function, it don't got no critical new inflection values. That's good work. And then you finish sneaking in where you were going to be going. All right, don't trespass, by the way. I'm not saying that. How much time do we got? 11 minutes. Okay. I don't know if I'm going to do all of these because it gets pretty redundant, but let me go ahead and do, let's do this one here. I want to do F, and now I need to kind of pressure wash that graffiti, get it out of the way. There we go. What's the domain of x to the fourth? All real numbers, yeah. So, G prime, it's 4x cubed. What's up, G prime? We're just passing through. We get 12x squared. Now, where is G double prime equal to DNE? Never. Where is G double prime equal to 0? At x equals 0. Does that mean there's an inflection value at 0? No. That just makes it a PIV, right? You're going to be baited and tempted on multiple choice questions. Just because you have a value of x that makes the second derivative 0 or undefined, even if it's in the domain of the function, it doesn't make it an inflection value unless the second derivative changes signs there. So you actually would need to test. So here we go. There's no discontinuity, so we make our little number line chart. Here's 0. How about negative 1 and 1? When you plug them back into the second derivative, what do you know about the second derivative? It's always positive. So it's a PIV, but is it an IV? No, no. So there's a nice example of not an IV, but still a PIV. And of course, you know that right away because x to the fourth looks like x squared that actually is a little bit older than x squared. It's sagging a little more between negative 1 and 1. Okay? That's what happens when the years get up on you. Yeah. Yeah, there we go. All right, we're going to stop right there, and maybe I'll do a couple more from this section tomorrow, maybe G and H, and then we're going to get to the second derivative test, okay? So our test is next when? Tuesday, and it's up through this section right here.